Good afternoon again. The recording has started. So we will cover two topics today. Both of them are related with discrete event simulation. So the first topic that we're going to cover today is on comparing two systems. So let's just recap what you have learned about discrete event simulation so far. What you started off with is to learn how to write a simulation program. And we have done that last week. You know how to structure a program to handle the events. That's why they're called discrete event simulations. Now, what you have also learned is that from simulation program, you cannot get the exact mean response time, but you can get a confidence interval. That's what we covered on Tuesday. And on Tuesday, you have also learned how to compute the confidence interval. One thing that's important is what's the width of the confidence interval. The narrower the width, it means the more accurate results you are going to get. Now, and what you have also learned is you can get more accurate, you can reduce the width of the confidence interval by simulating for longer. Also, you can get that by using many more independent replications. No. So what you're going to learn today will be you are going to learn how you can compare two systems in a statistically sound way. So that's the message that I was just about giving you. But when we want to compare this, we want to do it in a scientific way, and that's what we are going to cover today. Now, so before we go and show you how you can compare systems, what I want to show you first is it can be tricky to go and compare two systems. Okay, now you have already seen this slide on Tuesday. So this slide comes from a revision problem that I gave you for week 4B. So the exercise was to simulate two queues. First one is an MM1 queue with a certain arrival rate and a processing rate of 1. And the other one is an MM2 queue with the same arrival rate, but the processing power for each server is only half. But if you compare the total processing power for the two different configurations, then what you find is the total processing power for both of them is 1. Now, you have seen this problem when we were talking about MM1 and MM2 queues, and you know that theoretically, the MM1 queue is going to have a lower mean response time. So now, and so you have seen this graph, and so what we did was we carry out the simulation 10 times, and so you have simulation 0 in that 0 to simulation number 9. So that 10 simulations. For each simulation, we record the mean response time, which is shown in the vertical axis. Now, so if you talk about simulation with the index 0, then what you find is the red dot, which is coming from the simulation results of MM simulation, and the cross, which is the simulation results from MM2 simulation. The MM1 simulation has a better result, but if you look at experiment 1, also MM1 simulation has better results. Now, but that's not always the case. If you look at experiment number 2, then MM1 actually has a worse mean response time, so experiment number 4. And also, if you look at it, experiment number 9 as well. So in 3 out of 10 experiments, then we are actually not getting the answer that we expected, because what we know is theoretically, the MM1 queue has a better mean response time compared with the MM2. So that does not sound very good, because it means 30% of the time on average, we are going to make a mistake in our decision. So we do not want that. So this is the problem that we want to look at. And that's to motivate you. Just when we try to compare systems, that can be difficult. But I will also offer you a way out later on how you can make it easier for you to go and compare systems to get more accurate answers. All right, so let's move on now. So why do we do simulations? So we do simulations for one reason, for many different reasons, but one reason why we want to do simulation is we want to compare two systems. Now, if you go back to what we learned earlier on when we were talking about operational analysis, there was a question that we discussed in class. That's the thing about modification analysis. The thing is, do you want to switch from the present day, the system that you have now, to a different system? So this is what we want. And so what it means is you want to see whether the new system is going to give you better response time or not. So this is a question, again, on comparing two systems, and that's what simulations can be used for. So you may have alternative ways to go and do to go and organize your systems or manage your systems. Will that be better? And so these are questions that you would like to answer. Okay. Now, so that is the questions that we were looking at earlier on the previous page, comparing an MM1 system against an MM2 systems. Now, so you're quite used to comparing a single number, okay? And it's because, say, if you, for MM1Q, you can go and compute what the mean response time is. For the MM2Q, you can also go and compute what the mean response time is. Now, once you have the two mean response time, you see which one is smaller, that you know that system is behaving, having a better performance. So it's easy for you to go and compare two systems if you can have a formula to go and compute the mean response time now. But the thing is, when it comes to simulations, I've already told you that you are not able to get one number. And so you don't have a formula, and simulation is not going to give you an accurate answer. But what simulation can give you is a confidence interval. Now, so if you have confidence intervals from your simulation, how do you compare them? And that's what we want to talk about for this for today. Now, so we will continue to use this example of an MM1Q and an MM2Q as the example that we're going to use throughout this lecture. We are going to see how we can compare these two systems. Now, so we said that we are going to do the comparison by using simulations. So what I'm going to do is we have written these simulation programs. So I'm going to simulate the MM1Q 3 times. So I'm going to do 3 independent replications. For the MM2Q, I'm going to do the same. I'm going to do another 3 independent replications. Now, because for each system, I'm going to simulate 3 times. So what it means is for both systems together, I'm going to use 6 different sets of random numbers to go and perform this simulation. Now, what you have learned on Tuesday is that you need to go and remove the transient and then go and use the steady state part to go and estimate the mean response times. So here are the numbers. For system 1, the mean response times from the 3 simulations are these 3 numbers. And for system 2, the mean response times for these 3 numbers are these 3 numbers. Now, so what we do in order to compare them is we are going to pair them up. So what we're going to do is we're going to say we take the first experiment from system 1 and first experiment from system 2, pair them up. And so I'm going to pair up these 2 numbers. And then next, I'm going to pair up these 2. They both come from the second experiments for the 2 systems. I'm going to pair these 2. Now, so it's easier if we go and organize what we are doing in a table. Okay. So in this table, each row is 1 replication, and this column is the estimated mean response time of system 1. And for this column, you have the estimated mean response times of systems 2. So we pair up the numbers. So if you want, you can check these are the numbers that I showed you on the last slides, and these are the numbers I showed in the next slides. Now, so what we then do next is we go and do a subtraction. And so we subtract the estimated mean response time of system 1 from their systems 2. And so what it means is I take this number 8.8 something minus 6.8 something. So I get this number 1.9 something. And then the same thing, I do the calculations for each replication. And this minus 1.11 comes from 7.46 minus 8.57. Okay, so what you see here is now, so you have these numbers. Now, once you have these numbers, what we are going to do next is to go and compute the 100 1 minus alpha percent confidence interval. So I'm going to compute the confidence intervals, and quite often we use a 95% confidence interval, and so alpha is 0.05. Okay, so let's just say we go and compute the 95% confidence interval based on these three numbers. We have learned how to compute confidence intervals on Tuesday, and so you know how to do that. Now, so one thing you need to notice, we are not computing confidence interval from each system. We first do a subtraction. So we subtract the one from system 1 from system 2, and then we compute the confidence interval of the difference. So that's what we do. Now, let's just say the answers that you're going to give after computing a confidence interval. So the confidence interval has two numbers, and so it's P and Q, okay? And so what it means is P is the lower limit of the confidence interval. So P is the lower limit of the confidence interval, and Q is the upper limit of the confidence interval. Now, so because you have two numbers, P and Q, P can be a positive number, P can be a positive or negative number, Q can be a positive or negative numbers. Now, so what it means is we have three cases. The first case is the entire confidence interval P and Q, both upper and lower limits, are positive. The other possibility is both P and Q are negative. Now, the third possibility is Q is positive and Q is positive and Q is negative. And so these are the only three possibilities. Now, you may ask, don't you have one possibility that P is positive, but Q is negative? No, because for confidence interval, you always have the upper limit greater than the lower limit. So these are the only three possibilities. Now, let's look at a picture. Now, so let's just consider this possibility. Now, so I draw this axis, and this is 0. And so I consider the case that after you have computed the confidence interval, which is PQ, and we consider the case that both of the upper and lower limits of the confidence interval are positive numbers. And so what it means is you have a situation like this. The confidence interval is in this range, and both P and Q are positive numbers. Now, so what does confidence interval mean? What it means is there is a 95% probability that the difference that of the mean response times of the two systems is in this interval. Now, and if you look at this interval is always positive because both P and Q are positive. So what it means is there is a 95% probability that the difference is actually positive. Now, so what does that mean? Now, if there's a 95% probability that the difference is positive, and if you recall that this is how we computed the difference. The difference is the estimated mean response time of system 2 minus estimated mean response time of system 1. And so what it means is there's a 95% probability that this number is positive. Now, and if the estimated mean response time of system 2 minus estimated mean response time of system 1 is positive, then that is the same as saying estimated mean response time of system 2 is bigger than estimated mean response time of system 1. So, and what it's trying to say now is, the conclusion now is, there is a 95% probability that the estimated mean response time of system 2 is bigger than that of system 1. Now, so what does it mean? Is system 1 better or system 2 better, if that's the case? So if you know the answer, you can type it into the chat. If this is the case, do you think system 1 is better or system 2 is better? So you would expect system 1 to be better because system 1 has a lower mean response time. So this is how we draw the conclusion that's written in the slides here. If both of the limits are positive, then we say system 1 is better than system 2. Now, but we can't say for sure, okay? But only with a probability of 1 minus alpha, and so in this example of 95%. Okay. Now, you can make a similar argument to say if both P and Q are negative, then system 2 is going to be better than system 1 with a certain probability. Now, what happens if the lower limit, so the upper limit is positive and the lower limit is negative? Then we can go and look at this particular situation. So in this case, the confidence interval will look like this. The lower limit P is negative, the upper limit Q is positive, and so the confidence interval is here. Now, so we make the same argument. We say 95% probability that the difference is in this interval. And so what it means is 95% of probability that the difference is positive or negative. So we can't be sure. So it means there's a good probability that 1 can be better, but there's also a good probability that system 2 can be better. Now, so what it means is, if this is the situation, if the confidence interval looks like this, with that, if the confidence interval includes 0, then in this case, what it means is we say systems 1 and 2 are not different with this probability. Okay, so in this case, it means 95% probability. We can't tell any difference between system 1 and system 2. So what that means is system 1 can be as good as system 2, and that is the conclusions. Now, so one thing that you need to realize is, if you can calculate the exact mean response time using a formula, there are only 2 conclusions you can draw. Either system 1 is better or system 2 is better. So you can make a conclusion, or they are the same. Okay. Now, but if you compare 2 confidence intervals, the conclusions that you can make is system 1 is better than system 2 with a certain probability, or system 2 is better than system 1 with a certain probability, or you cannot tell the difference between them with a certain probability. Now, so that is the difference between making a decision using confidence interval and making a decision between using a formula. Okay, so these are the 3 possible outcomes. Now, so after explaining to you how we are going to make the decision based on that, so what we're going to do now is so we're going to compute the confidence interval of these 3 numbers and then see what the confidence interval looks like. Now, so if we go and compute the 95% confidence interval of the data on the last slide, then the confidence interval is minus 4.87 to 4.43. Now, so what we have is lower limit of the confidence interval is negative, upper limit is positive, and so we have exactly the situation that I'm picturing here. Now, so what it means is, with 95% probability, the mean response time of the 2 systems are a lot different. Now, so the summation results are telling us that the 2 systems are almost the same. There's no difference between them. Now, we do have a problem here, okay? Because from King theory, we know system 1 has a better mean response time than system 2, but our simulation results do not show that. So saying that, and so what it seems to suggest is the simulation results are pretty useless. We can't go and distinguish between the 2 systems. So what can we do? Have you got any suggestions? Maybe you think about some of the tricks that you have learned on Tuesday, how you can control the accuracy of the simulations. So you may still recall on Tuesday, we learned about how we can control the accuracy of the simulation. There are 2 tricks that you have learned that you can try to improve the accuracy of the simulation. Okay, now, yep. So there is an interesting suggestions on the chat. One is to go and increase the number of replications. That's what we will do in one moment. Another possible way to go and improve the simulation results is to go and simulate it longer. Now, there's another interesting suggestion on the chat, and is to go and decrease the confidence interval. Yes, you can do that. You can decrease the confidence interval. Now, but then the thing is, if you decrease the confidence interval to 90% to 80%, yeah, you can. But then what it also means is we are actually giving up the chance of giving up the probability of telling something for more certain. Now, so if you can say something with 95% probability, is good, but don't you want to try to say something with a 99% probability or even not higher? Say if you have 2 formulas, you can calculate the mean response time. You're saying for sure, 100% you're sure. So the higher the probability, the more sure we are, that is an advantage. Okay, so quite often people want to say 90%, then 95%, but we can decrease this confidence interval probability to 90 or even 80, but then we are saying something with less confidence. They do have a price to pay. Okay, so we need to realize that. So what we do now is we follow on the suggestions, and we're going to increase the number of replications so that we can reduce the width of the confidence interval, and perhaps we can actually go and get trying to get a better conclusions. So just now we have only 3 replications, and so we're going to try to use say 5 replications, 10, 20, and 30 replications. Now, and so in this table, the column, there's an independent replications that we have 5. And in this column, I'm going to compute the 95% confidence interval, again, by of the estimated mean response time of system 2 minus that of system 1. Now, I've used 5 applications. The confidence interval becomes minus 4.95 to 5.02. Say we increase to 10 applications, the confidence interval become minus 1.5 to 2.8. And use 30, it becomes minus 1.27 to 1.98. When it's 30, the confidence interval becomes minus 0.6 to 1.8. Now, what we said on Tuesday is that if we go and increase the number of replications, we can reduce the width of the confidence interval. Now, so if you look at the confidence interval, when you're doing 5 replications, this is almost 10, the width, okay? But then if you use 30 replications, the width is about 2.5, all right? Now, so what it means is we are doing things correctly. Because we have increased the number of replications, we have indeed reduced the width of the confidence interval. Now, but if you still notice, all the confidence interval has a lower limit, which is a negative number, and upper limit, which is a positive number. So what it means is we still cannot conclude which one of them is better. So we have done our part, we have increased the number of replications, and we still can't tell. So what can we do? Now, so what I want to do now is we go back and look at how we did the experiments. Okay, What we did was we did our experiment with independent random numbers. So to explain that, I will show you a diagram. So this is our system one. It's an MM1Q. So we have the arrivals, and this is server. The processing rate of the server is 1. Now, and what we did was we obtained the arrival times through some random numbers. We obtained the surface time through some random number by generating random numbers for them. Now, how about for system 2? We do something similar. System 2, there are 2 servers, and so with a processing rate of 0.5 each. And we again, when we do system 2, when we simulate system 2, we generate the interval times to obtain the arrival times. And then we also produce sort of surface times. Now, so what you see here is the arrival times are different because we used independent random numbers, and the surface times are also different because we use some other independent random numbers. So what I want to point out is these have the same probability distributions, but they are different random numbers. So that is about what you see. And so the same thing with the surface times. They have but surface time is different because here the mean surface rate is 1, and here the mean surface rate is 0.5. And so the probability distributions for the surface times for the 2 systems are different, and they are also independently generated. So this is how we did the experiment. We generate random numbers independently, and that's what I taught you now. But that is actually the reason why we're not getting good results in this case. Now, so we are going to look at a different way to go and do simulations to help us to go and compare 2 systems. Now, so what I'm going to introduce to you is what I call the common random number method. And this is an alternative way to go and compare 2 systems under similar condition. Now, so let's see how you're going to use the common random numbers method. So system 1, and so I have done it in the same way before. I generated interval times to obtain the arrival times, and so these are the random numbers and surface times. Okay. Now, but when I go and simulate the MM2 system, what I'm going to do now is I'm going to do things differently. If you look at it, for these 2 systems, the difference is there are 2 servers, they have different rate. But what you can do is you can actually send in exactly the same jobs to these 2 systems. Okay, and that's what we try to do. So when it comes to arrival times, okay, because there's only one single stream arrival, I'm going to use exactly the same arrival time. So this is one thing I do. The second thing I do when it comes to surface time is I take the surface time here and I multiply them by 2. So the first job that's arriving to this system, it arrives at 0.06329. For this system, I use exactly the same job. It arrives at the same time. Now, but this server is 2 times as fast as this service. So what it means is, for this system, for system 2, if I'm going to process this job, that will take 0.3432 units of time in system 1. Then it will take 2 times as long to go and complete in system 2 because the rate of processing is half. So what it means is I can maintain the same job by multiplying this surface time by 2. So if I multiply 2 of this number, 0.3432, I get 0.6864. Now, so second job, arriving at system 1, it arrives at 3.6392. So second job, arriving at system 2, it has the same time. Now, but I need to adjust the surface time because the surface in system 2 is slower, and so I get multiplied by 2. 2 times 0.4320 is exactly 0.8640. Okay, same thing. So what it means now is, instead of generating independent jobs, I only generate these jobs once. I generate all these jobs once. I use these jobs to go and simulate system 1. And I will also be using exactly the same jobs for system 2. Now, sometimes you need to make some adjustment to your jobs. And the adjustment that we have to make here is that I have to multiply the surface times here by 2 to obtain the surface times for systems 2. And you can see that the arrival times are exactly the same. So we are doing it user. And so what it means now is, when I do simulation, these two systems are will be serving exactly the same jobs. Okay, now let's see what results we can get. Now, so this common random number methods, let me just make a few remarks. And so this what I've just introduced to you is this common random numbers method. And and the aim of the common random number methods is to reduce the variance. Just now, when we try to compare MM1 and MM2Qs, the variance is too large. And so what it means is the confidence interval is just too wide. Okay. Now, so a way to go and make this variance smaller is to go and subject them to similar experimental conditions. Okay. So that's what I said earlier. So for each replication, what we do is we only generate one arrival time and one surface time, and then apply this to both systems. But then you may need to make adjustments because of this surface rates can be different in different systems. No. And so in the next replication, what you do is, again, you generate new inter-arrival times and then new surface times, and then you apply to both systems. Now, if you use this method, what you will see in one moment is that you will be able to reduce the variance of the behavior. And especially in the case that these two systems are positive correlated, that means if you increase the arrival rate or increase the surface time for one system, you will have the same behavior for the other system, the same type of trend for the other system. That's what it means by positive correlated. And if that's the case, then you will be able to use this common random numbers method to go and reduce the variance. Now, let's have a look at some, let's apply this common random number methods to our problems. So again, we have these two systems, the MM1 and the MM2Qs. Now, so let's carry out 5 applications. And we call that in order to apply this method, for each replication, we're only going to generate one set of arrival times and one set of surface times. Okay. Now, and then we apply to both systems. That's what we do. Now, so here is a table summarizing the results. So each row here is one replication of the common random numbers method. So for replication 1, estimated mean is response time of system 1 is this number, 8.3 something, and the estimated mean response time of system 2 is 8.8 something. Now, for replications 2, these are the results. And now, and so I also got the results for that. Now, just now I said these systems have a very large variance, and you can see that. So over 5 simulations, the smallest number you can get is 6.88. The largest number you can get is 16.26. So it's actually quite a lot of variance that you see. So these systems that we are simulating do have large variance, so we want to control that. Now, system 2 also have a large variance. Now, as we recall earlier, what we need to do is we need to subtract we do the subtraction, we subtract the estimated mean response time of system 1 from their systems 2. Now, so if we do this subtraction, and so I calculate 8.8 minus 8.3, I get 0.5 something. And so I do these calculations for each replications. Now, Do you notice what? So one observations you can make here is that in this column, when it comes to the difference, this time I only see positive numbers. Okay. If you go back to the earlier slides, if you look at the difference column, I get both positive and negative numbers. So what you see here is here I only get positive numbers. And so what it means is for all the 5 applications, the estimated mean response time of system 2 is a bigger number. Okay. And system 2 is the MM2Q. And we know that you should have a higher mean response time. So these numbers are actually very encouraging, because if you just look at each replication, then the estimated mean response time of the MM2Q is actually higher. Now, so we did the same as before. We take these 5 numbers and then we go and compute the 95% confidence interval, and you get this as the result. So the 95% confidence interval of the difference is 0.40 to 0.69. Now, so what it means is we have the situation that is discussed here, that both the lower limit and the upper limit of the confidence interval are positive. So what it means is there's a 95% probability that the estimated mean response time of system 2 is higher. So what it means is there's a 95% chance that system 2 is actually having a higher mean response time. And so what we can conclude now is there is a 95% probability that system 1 is better. And that is the results that we are hoping to get. Now, so what this is telling you is that it's possible to go and use simulation to go and compare two systems. But it's important that you go and do your simulations in the correct way. Now, sometimes certain systems are hard to compare. So when you have some sort of hard to compare systems, you may need to go and use this common random numbers method in order for you to go and get accurate results. So this is what that's the message that I want to give you, that that for some systems which are hard to compare, common random numbers method will be something useful for you. Okay, now, so let's go and look at this common random numbers method a bit more. Now, so what we know is, what if we go and increase number of replications? Will that help us? Will we get the same answers? No. So in this table, the results for using different number of independent replications, and I'm giving you over here in these two columns, 95% confidence interval of the estimated mean response time of system 2 minus that of system 1. Now, so there are two different methods. One is we didn't use the common random numbers method earlier, and these are the results of the confidence interval. And say if you use common random number methods. Now, if you use 5 applications, you have already seen the results. If you don't use common random numbers method, then the result is inconclusive. But then if you use common random numbers method, we can say system 1 is better. Now, if you use 10 applications, you have seen this earlier, inconclusive here. But again, what you see is both the upper and lower limits of the confidence interval are positive. So again, it gives us the 95% confidence interval that the system 1 is better. Now, and so if you go on and do 20 and 30 replications, what you find is that you are able to draw the same conclusion, that there's a 95% probability that the MM1 system is better than the MM2 system. Okay, now, So these are the conclusions that you can draw. Okay. Now, so what we have shown you is we have shown you how to compare two systems by computing, by pairing the by pairing up the replications, do a subtraction, and compute the confidence interval of the difference. Now, so can you also, but is it possible to go and compare systems by just computing the confidence interval of each system themselves? Yes, sometimes you can do that. And that's what I want to show you here. So now, so what we want to do is we want to go, let's just say we have done our applications, and then we can compute the confidence interval for system 1 and system 2. Okay, and so can we use the confidence intervals for the mean response time of system 1 and system 2 to go and draw some conclusions? In some cases, you can. Now, so there are 3 different scenarios that we need to consider. So here I have the confidence interval for system 1, I have the confidence interval for system 2 here. Okay, now say and so here this dot here means the mean, and vertical bar here is the confidence interval. Now, so so this is the mean for system 1. That's the confidence interval for system 1, and this is the mean for system 2, and this is confidence interval for system 2. Now, one possibility is these 2 confidence intervals for the 2 systems do not overlap, and that's illustrated in this figure. So if this is the case, then you can say the mean of system 1 is higher than the mean of system 2. Okay, this is that will be true. So what it means is, if you have a situation like this, you can conclude that the mean of system 1 is better than the mean mean of system 1 is higher than that of system 2. Okay, now, so that's what you can conclude. Now, there is another case that we consider. In this case, the 2 confidence intervals from the 2 systems overlap, and the mean of a system is in the confidence interval of the other. So what it means is, if you look at this, this is the mean of system 1. It is inside the confidence interval of system 2 because it is here. And if you look at system 2, this mean is within the confidence interval of system 1. So in this case, what you can safely say is these 2 systems are not different. Okay, so it's similar to the situation described here. Now, there's one more possibility is that the 2 confidence intervals do overlap, but the mean of one system is not in the mean of the other confidence interval, and so the mean is here for system 1, and it's outside the confidence interval for system 2. In this case, this visual test is not conclusive. Okay, you don't know. So you have to go back and do the t-test, and t-test here means computing the confidence interval, the student t-distribution that we're talking about on Tuesday. Okay, so sometimes what you may want to do is go and just compute the confidence intervals for each system, plot it up, and this is a very nice visual test because it means you can actually safely say whether one system is better than the other. If you see this, now, so let's try to apply what we have learned just now on the previous slide to this particular example. Okay, so so if you learn computer networking, you know there are a lot of different protocols that people use, and different protocols can have different throughput, different results. Okay, so this is a piece of research that I did a while ago, and what we want to study is we have 3 different protocols. One is called WCMA, the other one is called SPT, and the third one is called RCAM. The name of the protocols do not matter. Okay, so so say for one test setting, we have this as the, this is the height of the graph, is the, what I'm showing you is the network throughput. And so the height of the graph, the height of the bar is the mean throughput for RCAM protocol. Now, this hairline shows you the confidence interval. So mean is here, the confidence interval is here. So for this protocol, for SPT protocol, then this is the mean and that's the confidence interval. Now, this is for one experimental setting. This is for another setup. These are the throughput and the confidence interval, and that's for another setting. Now, so now you have understood what the graphs mean. Now, what conclusions can you draw? Or are you able to tell me out of the three protocols, which one is the best? So are you able to say out of the three protocols, which one is the best? If you know the answer, you can type into the chat. So the idea is you have to go and use what you have learned over here. So the vertical axis here is throughput. Okay, so okay, so a few of you were thinking whether RCAM is better. Yes, indeed, RCAM is better. Now, first of all, this is throughput. So what that means is higher the throughput, the better. And so you want a protocol that gives you high throughput. Now, so if you look at the confidence interval of RCAM, it doesn't overlap with the other two. Okay, so it's always higher. Okay, and RCAM higher than 2 do not overlap. RCAM higher here do not overlap. So what it means is from here, you can conclude that RCAM is behaving better than the other two protocols. Now, from this graph, are you able to say whether SPT and WCMA, whether they are, what is one of them better, or you can't tell? What can you say? So, yep. And so you can't really tell. Now, if you really want to say something, yes, you may say for some circumstances, SPT is better than WCMA, but for some other circumstances, WCMA is better than SPT. Now, but in some cases, they are almost the same. Okay, you can't tell the difference. No, but you need to remember when we say better here, we always mean better with a certain probability. Okay, now it's 5 to 1 now. So we will have a break and then we will continue after the break. Okay, so what I will do is I will pause the recording. So we will resume at 5 to 1. So, so just before the break, you have learned how to compare two systems. One is to go and calculate. Now, so what you have seen so far is what you have, and so when it comes to doing simulations, So sometimes you may have to write your own simulation code, but sometimes you do not have to, because there are also simulation tools out there to go and help you to go and do simulations. Okay, now, so if you talk about okay. Okay, my apologies. There was a problem with the network at my place. So the connection was dropped. So now let me just check whether the recording is happening. Okay, the recording is happening. So I will continue. Okay. So can I just check that you can hear me and also you can see my computer screen? So if that's the case, please type it into the chat. Thank you. Okay, great. Thank you. Now, so that's where I was talking about. And so say what you can use simulation for. You have say you have an existing protocol number 1, and you have designed a new protocol number 2. And then what you want to do is you want to go and see whether protocol 2 is better. So in this case, what it means is you can use simulation to go and tell whether one protocol is better than the other, whether the one you have designed is better than the one that you have now. And another option is maybe you have 2 options that you want to compare, 1 and 2, and then you can use simulation to help you to decide which one of them is actually a better protocol. Okay. Now, so there are actually quite a lot of tools that that can actually help you to go and write computer program, so to write simulations. But one thing that is very important, and that's the message that I want to give you, is that doing simulation is not just about writing a computer program. It's very important that you go and analyze the simulation results in a statistically sound way. And by that, I mean you use confidence interval, you do t-test, or you use the visual test. It's important that you calculate the confidence interval, because for simulations, we can only tell whether something is true within a certain probability. Now, so as a summary for this part, what I want to say is simulation is not just about writing a computer program. It's important to make sure that the program is correct. It's also very important to go and analyze the results in a statistically sound way based on using confidence interval. Now, but one thing is, a lot of researchers actually don't go and calculate confidence interval. And there is, if you go and read what this paper is talking about, a lot of simulation research, people didn't calculate confidence interval. Now, those people didn't know what the right way is, that you have to go and calculate confidence interval. But now you have gone through this class, so you know what's the right things to do. So you should be doing that. So this is so much about this part. So what I'm going to do is I'm going to move on to a new section, which is also on discrete event simulation. So let me just pop up the okay. So this is the last part of the discrete event simulation that we're going to talk about, and this on generating random numbers. Okay. So what we have done is in week 4B, last Thursday, you learned how to structure a simulation. And then on Tuesday and before the break, you learn how to do statistical analysis. So what we're going to do for the rest of this lecture is, I want to give you some background on random numbers because you are going to use them and how they are generated. And we're also going to show you how to generate random numbers of any probability distribution. Now, and I also want to introduce to you the idea of reproducibility. Now, you may ask, say, the Python random library, yes, you can generate many different random numbers for many probability distributions. But sometimes you may want to generate random numbers from a probability distribution that the Python library doesn't have. So in this case, you need to do it yourself. And what this lecture is to show you how you can actually go and generate random numbers from any probability distribution. Now, so to start with, we want to go and see how you can generate random number in a programming language, in the C programming language. So in C programming language, there is a function called rand, and you can go and use it to generate random integers. Okay, and these integers will be as small as 0, as big as a fixed number called rand max. So I have a piece of code which I've also given you, and so if you compile it and run it on your computer, then it will generate random numbers, random integers in this case. So let me pop my terminal up. So so I have the files in this directory. So I've already compiled the file, and then if I go and run the command, then it has generated these 10 random integers. Okay, now, so this is what you can get now. So what I've done is I've used this program instead of generating only 10 random integers. I've generated 10,000 of them. Okay, so these random integers as small as 0, as large as about 2.2 times 10 to the power 9. Now, so this is a histogram of the 10,000 random numbers that were generated, and so these bins of a certain width, and so if the random number are generated within the bin, then I will count it once. And so on the vertical axis of the frequency of getting the random number in a certain bin. Now, because these bins are uniformly distributed, so what it means is, and I've sorted them into 50 bins. So what that means is, because I've generated 10,000 numbers and 50 bins. So what it means is, if it's truly randomly distributed, I should expect to get 200 numbers in each bin. It's a 200 this level. Now, what you see here is some bins have more than 200, some bins have less than 200, but roughly speaking, it seems to be correct. So from this graph, you may say the numbers are almost uniformly distributed. Now, and so how does this random number, how does the random number generated in C work? The random number generated in C is called a linear congruential generator. So I just short form it to LCG. Now, and so LCG will generate a sequence of integers, Z1, Z2, and Z3, according to the recursion. So given zk minus 1, you multiply it by a and then plus c, compute the module m, and then that will become zk. And so so there are 3 parameters you need to choose: a, c, and m. Now, so if you choose a, c, m, and z1 appropriately, then you can get a sequence of semi random integers. Now, so let's go and try and do that. Let's just say a is 3. C is 0, M is 5, and Z1 is 1. So let's use these parameters and see what the recursion looks like. So, so Z1 is 1. So Z2 is given by A times Z1 plus C mod N. And so A is 3, and so this is 3 times Z1 is 1 plus C, which is 0. And then this is mod 5. So what it means is it will be 3. Okay. Now Z2 is 3, and so what it means is Z3 is A times Z2 plus C mod M, and so it means A is 3, Z2 is 3, C is 0, and so I don't write it. So this is again mod 5, and so what it means is it will give me 4. Now Z4 will be, oops. 3 times 4 mod 5, and that will be 2. Okay, Z5 will be 3 times 2 mod 5, and that means it will be 1. So what you see is it actually goes back to 1. Once it's gone back to 1, it goes in a cycle. And so what you see here is this generator actually goes in a cycle 1, 3, 4, 2, 1, 3, 4, 2. Now, if you really want random numbers, this cycle is of course not very interesting because you are going to go and get the numbers repeated. So what I want to demonstrate to you is, if you use this generator to go and generate random numbers, the sequence will repeat now. And when you repeat, you will have a cycle of n-1. So just now we have n equals to 5. And so what you see is after 4 numbers, you to get a repeat. Now, certainly you don't want the random numbers to be repeating. So what it means is you need to choose m to be a very large number. Now, so C, m is the number to the power 31, which is quite big. Now, so, and if you use a large m, the cycles will only repeat after a lot of numbers have been generated. So that's why you will see that the numbers are parity to random, because you're only looking at a small section of it. Now, so one thing you need to know is the correct name for talking about, it's not correct to say random numbers. The correct term for it is pseudo-random numbers that we are generating. They look like random, but they are not truly random. And so that is the correct technical term for it. They are called pseudo-random numbers. Now, so there is another idea about these random numbers, is that this is the number called a seed, okay? And so what this LCG does is, you have seen is, it generates a sequence of integers starting from Z1, you go to Z2, and then Z3, according to a certain formula. Now, the first number that you put in, Z1, is called a seed, okay? Now, so by default, C uses 1 as a seed, and to start the to generate the random sequence. Now, so just to demonstrate that, earlier I've generated these 10 random numbers. Now, so what I'm going to do is, I'm going to call the program again. And what you see is, it's giving me the same random numbers. It's each time when you start the random number generator in C, it uses the set, it starts with the seed 1. So that's why each time when you start the program, you get the same set of random numbers. But that's not very useful, okay? Now, so one way is, you can say, you can ask the program to go and use a different seed. And so I've used a different, so there is a function in C called srand, and that is to go and start to change the seed, okay? Now, so I've written it in the program genrand2. So in this case, what I'm going to do is, I'm going to give a new seed. And so instead, let's just say if I use 1, then what you see here is, I get the same numbers as before. As I said, if the seed is 1, then I will get the same numbers. But if I change the seed to, say, different integers, and what you see now is, I'm actually getting very different integers from this generation. So what I've done is, I'm going to, if I use genrand2, this program, I'm saying is, I specify what the beginning seed is. Now, it's quite clumsy if you want to go and do many replications and you have to specify your own seed all the time. So one way is, you go and use the current time, the time that you start the random number generator, and use that time to go and generate a seed, okay? So if your programs are running at different times, then you will get different numbers. So that is the program that I have in genrand C, which I've also given to you. No. So 3 here. So, and so I have these random numbers, which are different from what you have seen before. So if I do it another time, and what you see here is these numbers are also different. So it means each time when you run, you get a different set of random numbers. So you can go through the C programs later on. But that, and so the key idea I want to introduce to you is this idea of seed, this idea of pseudo-random generators. Now, so with C, you can generate random integers between 1 and this very big number. Now, and if you divide these numbers by the maximum that you can get, then you get uniformly randomly distributed random numbers between the interval 0 and 1. Now, so in Python, what you can do is you can also generate uniformly random numbers between 0 and 1. And there are two different ways you can do it. You can use the random library, and that's a function that you can call to generate uniformly distributed random numbers in the interval 0, 1. Or you can use NumPy library, and that's the name of the function. Now, so these two, in Python, the random number generators are a lot more powerful than the one in C. Okay, so both of these two libraries use a random number generator called the Mazen Twister. And if you look at the period, is this number to the power almost 20,000 minus 1. Now, this is an astronomically big number. If you do the calculations, it means, okay, it has a period, and so you repeat. But if you are going to use 10 to the power 9 random numbers in a second, the sequence will only repeat after this many years. So there's no chance for you to go and repeat the numbers, except if you try to start with the same seed. Okay, so what I'm telling you is, if you use Python, you do have a very powerful random number library, and you can basically make sure that the numbers do not repeat. Now, so why do I tell you about uniformly distributed random numbers between 0 and 1? One reason is these uniformly distributed random numbers between 0 and 1 are very important. It's because if you can generate uniformly distributed random numbers between 0 and 1, you will allow you to go and generate random numbers of any probability distribution. So that is a very important message. It tells you that if you can generate these random numbers between 0 and 1, then you can actually go and get random numbers of any probability distribution. And this is what I'm going to show you now. Okay, so this is just a graph similar to one that's before. This one is from Python. So generated 10,000 random numbers using a NumPy library and check whether it's almost uniformly distributed. Same idea as before. I provided you with the code in this file, so you can have a look later on. Now, so let's see how you can go and generate random numbers from different probability distributions. So let's assume that you can generate random numbers between 0 and 1. Okay, and we want you to use these random numbers to go and imitate a fair contours. A fair con means the probability of a head is 0.5, and the probability of the tail is also 0.5. Now, so you can go and have half a chance getting a head, half a chance getting a tail by just generating these random numbers. Now, so my suggestion is to use this algorithm. First, you generate a random number u. If u is lower than a limit, then your output, you say, is the tortoise head. If u is bigger than or equals to actually the same number that I'm covering up here, then your output is tail. Now, my question to you is, what number should I use here so that I get a fair contours? So you know the answer, you can type it into the chat. So I want to use this algorithm to go and imitate a fair contours. So I generate a random number u. If u is less than a certain number, I say it's head. If u is bigger than a certain number, I'll put tail. Now, I want the probability getting head and probability getting tail to be both 0.5. So what number should I choose here? So that this algorithm will give me half a chance of getting head, half a chance of getting tail. All right, so the answer is you should choose 0.5 because you have random numbers between 0 and 1. If you choose 0.5, it means half of the time you'll get a random number less than 0.5. So half of the time you will output head, and the other half of the chance you will be big, the random number you generated will be bigger than 0.5. And so then you output tail. So that will be how you can imitate a fair coin toss. Now you know how to imitate a fair coin toss. We make the problem a bit more complicated. We want to see how we can go and imitate a loaded die. So we want to create a loaded die with this probability mass function. So we want a die that has 6 phases from 1 to 6. Probability of getting 1 is 0.1, probability of getting 2 is 0.2, probability of getting 3 is 0.1, so and so on. Now, and what I am going to claim is that you can use an algorithm like this. You can generate the random number u, and then if u is less than 0.1, then output 1. But why do I say that? Because u is uniformly distributed between 0 and 1. So the chance that u is less than 0.1 is just 0.1. So and so if the number is less than 0.1, then I'll put 1. Now I have all these numbers covered up, and I want to work with you to go and sort of fill in these to go and what these numbers are. Now, and so what is the interval? Now, if the number is less than 0.1, so I'll put 1. But if u is in this interval, that I want to output 2. Now, so what I will say is, if u is between 0.1 and 0.3, then I'll output 2. But why do I put 0.1 and 0.3? Now, because I've used the numbers less than 0.1 already, I cannot use them again. So I start from 0.1 again. But if you look at the width of the interval, here's 0.3, here's 0.1. The width is 0.2. And so that means there is a 0.2 chance that I will be getting a number between this interval, and the probability, I want the probability get it, giving me a 2 is 0.2. That's why I want to output 2. Now, so to output 3, I will repeat this as 0.3. But what is this upper limit I should use? So that there is a probability of 0.1, I'm going to output 3. Do you know the answer? You put it into the chat. Yep. So you want to have a chance of 0.1 in this interval. So what it means is you should treat this to be 0.4. Then the width of the interval is 0.1. So there's a probability of 0.1 of outputting 3. So you should learn by now, this should be 0.4. Now, what is the number that I should put here? So that there's a probability of 0.3 that I will output number 4. So what should be this number? So the answer, you can type it into the chat. Yep. So you put the number 0.7 here, then the width here will be 0.3. There will be a probability of 0.3 that you will output 4. So now you see the pattern. So this should be 0.7. And if you want to output 5, there's a probability of 0.1 getting 5. And so here you should put 0.8. And if U is bigger than 0.8, then you should output 6. And if you remember, all the numbers are less than or equals to 1. So there's a chance of 0.2 of outputting 6. So now you have solved this problem. Now, let's look at it from, let's go and compare with something else. Now, so this is the probability that you want. Now, I want to go and find out what the cumulative probability distribution is. Okay, and the cumulative probability distribution is, so in this graph, 1, 2, 3, 4, 5, 6. So I want to compute the probability that the die gives a value less than or equals to x. And so this is 1, this is less than 1. So probability the die will give a value less than or equals to x will be 0. Now, what's the chance that the die will give a number between 1 and 2, including 1? Then it will be 0.1, because there's a chance that you get a number 1 with 0.1. Now, if you look at 2, what is the probability that the die will give a number which is 2 or less? 2 or less means you can either get 1 or 2. So the probability of getting 1 or 2 will be 0.1 plus 0.2, and there's 0.3. So I have 0.3 here. Now, so I work out these two intervals. Are you able to tell me what this interval should be? That's the probability that you will get a number which is 3 or less. So what should this number be? So this number is referring to this interval. It will be 0.4, correct? So if you go and work it out, the probability of getting a number 4 or less, this will be 0.4, but then you need to now add 0.3, and so this will be 0.7 and 0.8 and 1. So you can work that out. Now, so I'm going to make a comparison. Now, so this is the algorithm that you have come up with, okay? And this is the cumulative probability function, okay? Now, so do you notice something? Here, for the algorithm, you're using the numbers 0.1, 0.3, 0.4, 0.7, 0.8. Here, on the vertical axis, you are using exactly the same sequence of numbers, 0.1, 0.3, 0.4, 0.7, 0.8. So you are using the same numbers as in the cumulative probability density, as well as in the algorithm that you use to go and decide on what the number on the die that you should be outputting. Now, is there a coincidence or is there something deeper? There's something deeper. So, but then I'm so using a graphical way to go and explain to you that about this concept. Now, so what I'm going to give you is I'm going to give you a graphical interpretation of the algorithm that we have come out with. Okay. Now, so again, this is the algorithm. This is the cumulative probability density. Now, let's assume that the number that you have generated is U, and U, the number you have generated, the random number you generated is 0.5126. So if you work according to this algorithm, what is the output? Maybe I'll repeat my question. U is the number that you have generated. Say you need to generate a random number for your algorithm. U that you have generated is 0.51. And if U is 0.51, what will the algorithm output? So if U is 0.51, so U, if you'll be within this interval of 0.4 and 0.7, it should be outputting 4. So that's also what a student has answered in the chat. So let's look at it in some other way using this cumulative function. Where's U? U is 0.5126, and so it's this interval, this point. Now, so what we'll do is at this point, I will draw a horizontal line, and then you will hit the cumulative probability curve at this point. Now, when you hit the curve, what I will do is I will drop a line to drop a vertical line down here. And if you look at it, it's actually the number 4. Okay. So what it means is you can actually use the cumulative probability density to help you to go and generate random numbers. So what you do is you generate the random number u, and then identify the position on the vertical axis, draw a horizontal line, and then when you hit the cumulative probability curve, then drop a vertical line, and that is the random number that you need. So this is another way of getting exactly the same output of this algorithm. So this is what I'm trying to show you, and you will see that in one moment, you can use this method to go and generate any random numbers. Okay. Now, so the method that I'm trying to tell you is what people call the inverse cumulative density function. The lower limit must be 0, the upper limit is 1. And so now, so how do you generate the random numbers? So say for this particular fx, this is the blue curve here. Say if u is 0.7, then what's the random numbers that you generate? From 0.7, draw a horizontal line. And then when you hit the cumulative density function curve, you drop a vertical line, you read this value out, is 6.8. So then what it means is the random number that you generated has the value of 6.8. And that's how you use the cumulative density function. Now, so this is the more detailed description of the inverse transform method. So for this particular method, if you want to generate a random numbers with a cumulative density function fx, then you use the procedure. You generate a number u, which is uniformly distributed in 0, 1, and then you compute the inverse of u. Now, so the procedure that you are calculating, what we did was by drawing this horizontal line, and then dropping the vertical line when we hit the curve. This is effectively computing the inverse of this fx at the value of 0.7. Now, so let's apply the inverse transform method to the exponential distribution. And for exponential distribution, it has this CDF of 1 minus 6.1. Okay, so the cumulative probability density is given by this curve. So fx is 1 minus exponential minus x. And what we want to do is we want to compute f inverse of u. So let's just say this is u. X is actually the f inverse of u by drawing the horizontal line and then dropping the vertical line down. So if you have this relationship, then what it means is fx is the same as u. Now, but what is fx? Fx is 1 minus lambda x, and that should be the same as u. Okay, and then you can say exponential of this is 1 minus u. Now, so I will take log on both sides. So what it means is minus lambda x is log of 1 minus u. And then you can say x is log 1 minus u. Now I need to divide both sides by minus lambda, and so I have minus sign here, and I put the lambda here. Okay. Now, so what does it mean? I need to take away that. That is not, that should be a minus sign over here, just to make things correct. Okay. Now, so what does it mean is you generate a random number u, which is point between 0 and 1, and then you compute x according to this formula. So for every random number u, you compute x, that will be a number that you have generated. Now, so what this is how you can generate numbers that are exponentially distributed. So what I've done is I generate a sequence of random numbers that uniformly distributed in 0 and 1, 0 and 1. These numbers are u1, u2, u3, and so on. I then go and compute minus log 1 minus uk divided by lambda. Now, and the k is this will give you exponentially distributed random number with the rate k. Now, so I've actually written a program to generate this 10,000 exponentially distributed random numbers, but this time I'm not using a random library. What I do is I generate 10,000 numbers that are between 0 and 1, and then for these numbers I compute the log of 1 minus the random number divided by lambda. Okay, and then now, so if I run the program, you will get you be able to generate exponentially randomly distributed random numbers. Now, so I've run the program earlier and I generated this graph. Now, so this is the histogram of the distribution of the random numbers. And now the red curve here is the expected number of random numbers. Now, and so this is exponentially distributed. Now, so what you see here is the numbers that you get are quite close to an exponential distribution. And so now, so I've given you this program so you can go back and see how you can use the this to go and generate exponentially distributed random numbers. Now, what you will need to realize is the method that I'm talking about, the inverse transform method, you can use it for any fx or any probability density. So that's why it's a very powerful method, as long as you can compute the inverse. So if you can compute the inverse, you can use this method to go and generate numbers of any probability distribution. So I'm using exponential function as an illustration, but this method is general, and so you can apply it to other methods too. Okay. Now, so I'll finish on the topic of generating random numbers for any probability distribution. Now, so I'm going to move on to the next topic, and that is on the topic of reproducible simulation. Now, and you may recall that I've run this simulation program that we developed last week on simulating MM1Q. And each time when I run the simulation, I get different numbers. Now, I'm using a different set of random numbers, and so I get a different value for mean response time. Now, one thing that you think about is when we do simulations, it's like doing a scientific experiment. But if you do good science, what good science demands you to do is to come out with experiments that other people can repeat. And that's what we call reproducibility. Now, so say if you go and claim that your mean response time of your simulation is this particular value, other people should be able to reproduce your results. And that is good science. So it's important that your simulation results should be reproducible. So what I'm going to show you is you can go and make your results reproducible by storing the state of your random number generators. Now, so So to make the results reproducible, you're going to store the states of the random number generators. Now, so if you think about earlier, when we talk about the random number generator for C, there is a number called seed. And so if you know the seed, you will be able to generate the same random numbers again. Now, in Python, because it uses the Manchester, what you can do is you can go and store the state. Now, so what I will do is I will go back to, I will take the program CMMM1 that I've given you last week. Now, there are a number of lines that I have commented out, but I didn't talk about last week, so I'm going to talk about them now. So first of all, let me sort of run the program a few times. So you see the random number here is, this is using a new set of random number, 0.668. And then for the mean response time output, if I run again, then what you see here is I get different results, 0.660. Now, so what I'm going to do is I'm going to uncomment these 3 lines out. Okay, so so I import pickle because I need to store something in a file later on. So I use the function random get state to go and get the state of the random number generator. And then what I do is I store this state inside this file. Okay, and so what I do now is I run the program. Now, I mean, you get again a new result for the mean response time is a different number, 0.6592. Now, so what I will do now is I'm going to comment out these 3 lines. No. And if I go and run another simulation, I get a different number, 0.665. But now that's not what I want. What I'm going to do now is I'm going to uncomment out these 3 lines. Okay, I should also uncomment out this line. Okay. So what I do is I load, earlier on, I store the state of the random number generator inside this file. I'm going to load this file again. I store in the variable rand state, and then I say rand state into random set state. So what it means is I'm loading the old state of the random number generator or the seed before that, and I set it as the state of my random number generator. Now, let me run the program now and see what the effect is. Now, what you see now is this number that I have is exactly the same as the number, the mean response time that I got earlier. So if I say I run it again, you get exactly the same results because I'm starting from the same seed, I'm starting from the same random state. I'm able to repeat the experiment. So what it means is you have a simulation program, you store the state, you give your state and simulation program to someone else, someone can actually reproduce exact results that you have. So that is to go and make things reproducible. And that's the key ideas. So these are the lines, and they are actually in the file CMMM1 that I've given you last Thursday for week 4B's lecture. So but I didn't talk about that because you wouldn't have understood, you haven't learned about random number generators at that moment. But now you do, so you understand what I'm trying to do now. Okay. Some remarks about the random number generators that you have in Python. So there are 2 libraries that you can use. You can use NumPy or you can use the random libraries. Both of them use the same type of random number generators based on Manchester, but you need to know that they are 2 different generators. So they are separate. So this here, I showed you how I'm using the random library here. So and so you know how to get the state. Say if you use a NumPy library, you want to get the state. This tells you what commands or functions you can use to go and use for the NumPy random library. Okay, so as a summary, what we have done in this hour is to give you the basic concept of these pseudo number random generators. You have an idea, you have some idea, some overview of how it works. And the key thing that I would like you to learn is to use the inverse transform method so that you can go and produce random numbers from any probability distributions. Now, we have also gone through the topic of reproducibility and why we need that and how you do it. So these are some of the references. Now, so what happens is sometime this week, I will post the project on the course website. The project will be on simulations, and we have gone through all the lectures on discrete event simulations, which means you will be ready to go and work on your project once it is released. Okay. Now, next week is week 6, is flexibility week, and so we are not going to have any lectures. So we have a break of lectures for 1 week. We'll resume on Tuesday in week 7. So I wish you a good break, and I will see you again in week 7. So if you do have a question, you can type into your chat. Otherwise, I do have a consultation at 2 o'clock. All right, so much for now. I will stop the recording.